Most of the vibration problems that you'll see in the field, the problems are related to bad suction conditions. What do we want between the tank and the pump? Straight pipe. It can make a few turns. A pulsation dampener. If I build a good suction line, I probably won't need a suction dampener. I might need one on the discharge. But if I get straight, big pipe where I keep that suction velocity low, generally below less than a foot per second, I'll eliminate a lot of the vibration problems that come from positive displacement pumps. And then back to our drawing, right there, what kind of reducer am I using to come into the pump with? Concentric or eccentric? Eccentric, so that I don't pull gas into the pump, keep a full column there. And then, so when we select our pump, our total capital cost plus our operating cost determines the type pump we'll select. Here's an example of the pumps and their foundations. Real quick, we've got a force. Let's go over here first. We've got a large chunk of concrete under the pump. There's a weight vector that sits on it, and there's a vector for the motion created by that plunger movement. The resultant force doesn't go through the center of the block. Even though it's sitting on a big chunk of iron, the resultant's here. We can get by with a smaller one. The resultant force coming down here goes through the base, and the base will absorb that motion. So you don't have to be a civil engineer. You got to know one, and then he design that base for you. Let's talk about distribution lines. They're real simple. We go from the pump out big pipe until we get to headers. We get to headers, then we go to smaller pipe, and then we can go from our smaller pipe, we connect it to an injection well. Simple concept, right? If I didn't tell you that was an injection line, we could say we tie wells in that we're producing, we take them to headers, we make these gathering lines, and we take it into a separator. Injection lines. Buried steel has to be insulated or wrapped or coated, especially in caliche. Everybody knows what caliche is. It's that clay-like material that we make a lot of our drilling pads out of. It's common material in West Texas. It's not so common in South Louisiana. They use crushed oyster shells for pads. But either way, with the clays that are in caliche, we wrap that steel pipe to prevent the external corrosion. We need to keep lines away from old drilling pits or where old tank battery locations have been. When you're doing your water flood design, remember you're going to be putting in individual tank batteries. There's going to be pads that later you're going to put in, and you're going to be running lines. When you run those lines, you don't want to go through these old tank battery locations. There's lots of things spilled, and the soil can be contaminants for external corrosion. Fiberglass pipe is nice, it's corrosion resistant, but it has to be padded before you put it in the ditch. You need to lay a few inches of sand in there, and then you need to cover it with sand before you start throwing in rocks and old hickory bush and everything else that they'd fill a ditch with. If you put rocks right next to the fiberglass, as vehicle traffic goes over it and all like that, you're going to punch holes in it. So the fiberglass has to be padded. Yeah, it's nice for corrosion, but it's going to cost you. There are no free lunches. GRP, what's that? That's glass reinforced pipe. So that's a fiberglass is what generically we call it. This glass reinforced pipe has to be painted to avoid UV deterioration from sunlight. The fibers that make up that fiberglass are held together, and it literally takes that glue apart. And so unpainted fiberglass will deteriorate. Piping has to be purged before you start it up. You'll leave piping out on the ground. It needs to be purged. It needs to have water run through it, air, whatever, to get all the rattlesnakes, welder's rags, hats, fingers, whatever might have been left in that pipe. And then here's a recommendation on minimum velocities to go through a pipeline so that we don't let solids accumulate in the bottoms. Let's keep it to a couple of feet per second to keep things moving as we go through. We'll catch it in filters or strainers. Metering. We want to meter several points in our water system. We need to know total water volumes that are coming out of our injection stations. What's the total volume going to each header? What are the individual well volumes? How much water am I buying? And then what's my produced water volume? How much am I putting in there? So you've got to do a material balance around this whole system. You need to meter all of those points. And you will find out that the sum of the meters doesn't equal the whole. So there will always be errors in there. The more you spend on meters, the less that error will be. But you've got to find a place you can live with on economics. You want to place a strainer upstream of that meter. So if you do get debris coming down the line, you don't tear the guts out of it. The strainer will catch it before it gets through there. Liquid must not go below the last separation pressure, or you'll break gas out of it, and that gas is going to spin that meter and give you inaccurate readings. So tank, meter, control valve is the ideal way to do it. Or test separator, meter, dump valve. So we keep that gas from breaking out of that meter as we measure it. And then master meters, those are the main meters around a header, or at a header. Need a bypass line around it. Here's our master meter, say it's a 2-inch meter. We've got a line built around it that we can take this out of service and either replace it or repair it, and we can still keep water going. We use that mostly on the headers, but on an individual well meter, you probably wouldn't build a bypass. By the way, if we look at an injection manifold, where did Oxy have their meters? At the injection manifold or on the wellheads? Do you remember? We stopped at a well, right? What was at that wellhead? There was an injection well, wasn't it? And there was a meter on it. So the design I'm talking about says let's place the meters on a header. Back there on our distribution system where we have a header, I've got 10 wells. If I want to adjust the rate on any of them, I go to the header and I can adjust and balance there. If I have my meters out on my well, I can still adjust and balance, but I've got to go to every well and adjust a rate. So everybody has reasons for doing things the way they do. But if I had a choice, I would control from a single point on my header, put all my meters there, all my control valves, and then just send the water to the wells, rather than going to the well and adjusting. You wouldn't do both. That would be a duplicate redundancy. So on a manifold, we come out with this is looking down the end of that manifold, we come out with a shutoff valve. Here's our strainer. We go through the meter, and then here's a flow control choke. They also had a small flow control at the wellhead. And then our line going on to the well. That flow control, most of the time, will look something like this. We've talked about chokes, and most of them you've seen have been on the big wellheads, where they're a cone, and you screw the cone in and out. The flow choke on a water well will probably look more something like this. You have two plates. They're fully open when the holes in a fixed plate and a variable plate are aligned with each other. As you rotate the variable plate, you change the opening allowed for flow going through those holes. And then finally, you can rotate them so that the holes in the fixed plate aren't aligned at all with the one in the rotating plate, and you're shut off. You don't ever want to use a choke for a shutoff on any kind of application. Don't depend on it for a shutoff. The choke is what will take the erosional wear. And so if you're on a wellhead, you want to make sure you close a valve that gives you control of the well. The choke can be closed, but don't count on it. This is the strainer. The flow goes through in this direction. Looking at it cut open and reversed, the flow would go through here, capture your debris and junk, and then on out to your meter. This is a turbine meter. These haven't changed in the last 50 years that I know of. But cutaway view, it's like an airplane engine in there. You've got a rotor that spins. Each time it spins, it catches a discrete quantity of fluid. That spinning motion is picked up by the magnetic detector, and we get a measure of flow through there. We size turbine meters. Some of you expressed concern about there was a 1-inch meter in that line that we looked at. Looked a little tiny, didn't it? And they told us that 200 to 500 barrels a day would be going through that. So let's look. It was a 1-inch meter. And here's our barrel per day rate in this column. It says a 1-inch meter will handle 170 to 1,700 barrels per day. With what kind of pressure drop? Doesn't say, so we got to go to our sizing chart. This sizing chart I know hasn't changed in 45 years because I copied this out of a book that I had and I compared it with what's online now. And the only thing they've added now is what's online is flow rate in gallons per minute along with what's in here, or gallons per minute along with what's in here for barrels per day is the only change I see in the lines. They're still the same. So let's look at 500 barrels a day. This is a 1-inch meter. Along the top, we've got barrels per day rate. Along this side is PSI on a logarithmic scale. At 500 barrels a day, if we come down and we cross 1-inch line is right about there, that highlighted line. Come on, 500. 1 inch right there. And we read over, and how many PSI pressure drop is that? 1 PSI. And they had 2,300 back on the injection pump at the station. So that little 1-inch meter isn't hurting them at all. Just yeah, you can meter oil, water, gas. We've got samples of all that at OTC. So, simple design, quick and easy for turbine meters. Wells and wellheads, and we've got to push through here too because we want to do a little looking at some tank battery design as well. Our wells, you've got a choice when you make injection wells. You can drill new wells or you convert existing wells to injection. Several things to think about when you convert an old well to injection. What condition is the casing in? Where are the perforations in that well relative to the zone I'm going to be wanting to inject in? Do I have to alter those? Are the perforations plugged? Is there any possibility they might have scale, wax, paraffin, bugs, you name it, on those perforations? And in general, is there fill in the well bore that's going to have to be cleaned out? So if you're doing your economics on your well, you can drill a new well for certain cost, but just because I've got an existing well bore doesn't mean it's going to be free. There's certain costs that have to be incurred to get it going. A wellhead hookup, if we've got all the others set up at the header, will come into the well through a control valve or a shutoff valve. This is a unit wellhead assembly that contains a check valve, a lubricator cap, and a master valve for the well. They can all be bought as one, or you can make the individual pieces. This is all you'd need at the wellhead if all that other equipment's at the header. When we convert the injection well, a couple things to consider, or whenever we set up the injection well on a new one. This is our production casing. We've got tubing. We're set on a packer. Here's our perfs down here. You need to leave some room 50 to 100 feet below the packer and above the top perforation. What's a spinner survey? You ever heard of spinner surveys? That been covered anywhere? There's tools that we can run down hole in an injection well and determine flow rates into perforations. And so we lower on a wire line a tool down here, and we can calibrate that tool if we've got a section of casing that we can put it in that doesn't have perforations in it. So if we allow that 50 to 100 feet below the packer but above the perf, we can lower that spinner in there, we can set our injection rate, and then we can get a reading on that spinner of what it's going to read in blank pipe. Then we know as we go down to the perforations where we're injecting into them, if we're reading different numbers, then we've got a good idea of what the base is. In blank pipe, we can do what the percentage is that may be going through the perforations. The packer needs to be set in part of the cemented interval of the production pipe. Hopefully your production pipe cemented all the way up, but that packer needs to be set where the pipe is cemented. Internal tubing can be internally lined, but you have to be careful of the lining that you put in there because some of it will allow gas to seep through. If you have any hydrocarbon gas or if you have CO2, and so those gases can permeate those linings. I've seen them permeate the lining, then the lining collapses inside the tubing and it becomes a big mess to clean out. The other thing to consider is the metallurgy of the ID of that packer. Even though the tubing will be stung into it, that metallurgy may need to be stainless steel, even though the rest of it's carbon steel for corrosion protection. And finally, the well needs to be cathodically protected. This is something new that's just coming into play in the Permian Basin. There are a couple of other of the unconventional shale projects that this idea may fit, but it hasn't been tried out yet, but it is coming in the Permian in a big way. And these are midstream water companies. So in our oil and gas production operations, taking the oil and gas out of the well is upstream production, right? Refineries, chemical plants are downstream. What goes midstream in production? Huh?
Gas?
Yeah, gas plants, pipelines, those can be considered midstream entities. But what about water? There are now midstream companies that are setting up to handle water. And what they're doing, this is the same diagram that I showed you before, they're laying these pipes in here, building frac ponds, and they're telling operators like you want to buy produced water for a frac. I've got a system now running from here to there, and I'll sell you water off of my system at so much a barrel. They will do things like, you've got a producing well that has some water you need to dispose of it, but it got a disposal well way over here. You don't own the land in between. The midstream company comes in and says, I'll build that line from your producing field over to where you have disposal. Give me your water here, I'll take it over there for you. Just like a pipeline company would do gathering or take it to a plant. And so these midstream companies are looking at all this recycling and treating. And they're rubbing their hands like this if they look at the frac volumes, the drilling water volumes that are going on in a play like the Permian Basin. It may work in the Bakken, it may also work in the Oklahoma stack plays, where they have lots of water that has to be moved around. So these midstream companies are coming in, and they're setting up shop to handle water, produced water. They're going to be able to buy right-of-ways, secure that, where I'm a smaller operator, I don't want to have to mess with it, I can turn that over to them and let them handle that business for me. These are frac ponds that they typically are building, the midstream companies and the large operators. These hold about 500,000 barrels each, and that's roughly 10 acres. Our OTC, the fence around it, is a fenced area of 10 acres. So imagine the OTC dug out to a depth of 15 feet and fill it with water. And you'd have one of these frac ponds. And one of these frac ponds. It's got multi-layers of like rubber mats that are laid out. Between the layers are detectors. If any water leaks through there, it sends an alarm, a sensor that they've got water leaks. So these are elaborate, they're not cheap. But the midstream companies are laying in facilities like this. See here in the background's another one. And that big pipe like this is going in there. This is that first picture I showed you, the one the company's doing. That's 36-inch diameter poly pipe. Most of the time when we use poly pipe in the oil field, we use 2-inch or maybe 3-inch. And this stuff they're laying to connect all this together is literally, they're moving hundreds of thousands of barrels a day of water through 36-inch pipelines. Takes a pretty good ditching machine. I hate to shovel what that's going. The transfer pumps are interesting too. These are large centrifugal pumps. Some of them are mounted on trucks because there's people that'll rent you a pump just to get out of your frac pond over to your frac job wherever you're going. And notice here, this is their suction manifold. They've got 3 probably 12-inch pipes going into a manifold just to feed the suction of a centrifugal pump. Imagine how much water they're moving with that. Because these are diesel engines or gas engines, several hundred horsepower sitting right here. And then where permanent ponds are being installed, they're putting these vertical centrifugal pumps in at stationary points along the line where they're not being moving around. So all of this is a new business. It's, in the past, we've had water disposal companies that would maybe set up a mom and pop shop along the side of the road, and they'd have a well and some tanks, and you'd see trucks in and out of there. But nothing to the extent of what's going on now with the unconventional developments and these types of businesses that are now coming into play. So that's a need to know. If you go to work for one of them, you're really going to study fluid hydraulics. Let's talk about the facility design class. There were a lot of questions about tank batteries. How do I put them together? What goes first and what should I do first? On any major project that you have, the project, you need to understand what's my basis for design. So I've worked on projects either internationally or in the deep water Gulf of Mexico, where the first thing that was handed to the facility engineers was a design basis. And that comes out of a reservoir engineering shop generally. And they say, here's what we're going to do. We're going to produce this much oil from these wells. They're going to be stationed here. We want to produce this much oil, this much water, this much gas. Here are the fluid properties for all of these flow streams. And you hand that over there to the facilities engineer and they say, build that. That's all the direction they give them. So you're petroleum engineers, you're going to be on one side of that fence, or maybe you're the small company and you're both sides of the fence. So whether you're the reservoir engineer, you've got to understand what the design engineer needs. If you're the design engineer, you need to understand what the reservoir engineer is telling you and where you can tell him and her, or maybe give them some pushback that, what if I change this or that? Will that still work for you? So just because you're a reservoir engineer doesn't mean your facility capabilities have to stop. You're never going to use them again. Because through the course of your career, you're going to be on both sides of this fence, and sometimes more one way than the other. Part of my job one time was as an engineering manager, and we were designing projects around the world. And then we were doing them with multiple companies involved, large companies, small companies. And we would have a kickoff meeting we had for one deep water project, had a meeting of 50 engineers. It was, about half this class size, from about 7 different companies, and we all had to talk to each other. Just getting the common language down was a problem. So, on a facility design basis, this is kind of like a 1, 2, 3. Let's get our production rates. What's the initial rate going to be? What's the maximum rate going to be? What's the trajectory of that production through the life of the project? Because I got a design to handle all of that. And the maximum rate may not be the first rate that I see. It may come later in the life. When's that going to come? Gas production, MCF. What are my gas sales rates? What does my contract say my line pressure is going to be? What impurities have to be removed? Oxygen, nitrogen, H2S, helium is an impurity, CO2. Helium, by the way, the last I saw, was selling for $75 to $100 an MCF. And there's not much of it in the U.S. A large portion comes from Russia. And so the security of the supply runs that price way up. It's real important for the making of nuclear weapons. A lot of other cryogenic processes involve helium. So you've got a waste product there that can be worth more per MCF than your natural gas is. Side point. Gas lift rates. What kind of rates am I going to need to put out through a compressor? And then my gas rates for my vapor recovery units. Yeah. Oil. Need to understand how many barrels of oil per day am I going to see at any given site. What's the API gravity? What's my sales line pressure if I'm on a LAC unit? Why would that be important?
Does it need to go to the pipeline after the LAC unit?
Yeah, it goes to a pipeline. So
Keep that enough pressure?
yeah, you got to size the pump to get it in the line. Just like here on gas sales rate, the contract line pressure. Can I get it in the line? What pressure am I delivering at? Water production. How many barrels of water per day am I going to be handling? What's the specific gravity? The chloride content. I need to know all those things. They're important for corrosion protection. What's my metallurgy have to be? What other materials can I consider for that? And then for each vessel that we have, what are my oil, gas, and water inlet rates? You say, well, maybe going to a vessel that doesn't have any gas. Okay, the gas rate is 0. But what are my oil, gas, and water inlet rates for each vessel? What's my design temperature and pressure? And then what's my operating temperature and pressure going to be? And the fluid properties for each one of those that go in there. For each tank or series of tanks, and these are oil or water, how many days of storage do I need? And then what's going to be the capacity of each tank? If I need tanks fast, I'm going to have to put them on a truck. What's the biggest size tank I can put on a truck and deliver to site? Huh? Depends on where you live, but usually they're going to be 500, maybe 750s. And if I get bigger than that, I'm going to have to field construct it. Down in the Eagleford, I've seen 25,000 barrel tanks. In the Sahara Desert, we had 25,000 barrel tanks that we field constructed. That takes longer to build, so what am I going to have to do in the meantime? And then my disposition of fluids. Where will they go? Oil, water, and gas. Everything I bring in there, it's got to go through a material balance. It's got to go somewhere. Where am I going to take it? Battery vessels. Now here's the one y'all want hard and fast answers to, and I can't give them to you, but I'll give you relative designs. A separator is designed to separate gas from liquids. Duh, right? So it will handle high volumes of gas. Any liquid that comes off that separator, though, may require additional treating. So if I have a two-phase separator, I'm going to get gas, and then what am I going to get besides gas? And it's going to be what? The liquid. Oil and water. If I have just a gas well that produces some water, I'll just have water and I won't have to worry about oil. But if I got oil and water coming off that two-phase separator, I've got to do something else with that liquid stream. If I've got a three-phase separator, will the oil coming off of it be pipeline quality? Don't know. I may have to run it through something else. Will the water be clean enough to go to a disposal system? Don't know. I may have to do something else. Free water knockouts are good at handling high volumes of water. They're not good handling high volumes of gas. So they'll take water off if I got a little bit of gas. That could be the first vessel that I enter and use it depend on it for gas separation. If I have a free water knockout, the emulsions may not break out in it. In other words, I might have, it's taking free water, but that implies also that I've got to do something with water that separates that's not free and going to break out. So I've got to do something with it. A heater treater, and their other name is called an emulsion treater, can handle low volumes of gas. It could be the primary vessel if the gas volumes are relatively low. And it's designed, though, to break emulsions. It's not a water handling device. It's designed to break emulsions. A gun barrel is a step below a treater in the volumes of gas that it'll handle. The treater gets a little help because we're adding heat to do the separation. But when we don't have that heat in there, the gas that a gun barrel will take would be less than a heater treater. But a gun barrel will break emulsions. And the whole theory of that gun barrel is big, diameter, slow, get it through there, let it have time to separate. So a tank battery, and this one flows from right to left. Simplest tank battery, usually, if we come from a well, we go to a separator, remove gas, take liquids to a treater, break the oil, water to tanks, some gas is coming off the treater, and we go to gas sales. That was oil field 101, and until unconventionals came along, a whole lot of batteries through the country look just like this. And now we're getting more complicated, and all you're doing is adding vessels that fit your conditions. It's that simple. There's no hard and fast rules on it. Pressure drops, order of magnitude. A lot of questions have been asked about this. So the pressure drop in a liquid line, the wellhead to the first separator. You'll see wellhead pressures on the wells, order of a drop coming across there of about 10 to 150 psi pressure drop. And the lines can be 300 feet away or 2 miles. 2 miles seems to be sort of an upper limit we always bump up against about effective distance to have a well away from a header or a battery. From our separation going between a primary separator and a secondary separator, we're going to have 5 to 20 psi pressure drop across there just in the piping, getting from one vessel to the next. Treating vessel to a gun barrel, we're lowering down even more pressure. Again, all we're supplying pressure at these vessels is enough to push it to the next one. If I'm supplying pressure to push something to an atmospheric tank, I don't need as much pressure drop. I'm going to get some hydrostatic head help from whatever vessel I'm coming out of, but my operating pressure's got to be high enough to take that hydrostatic and a little oomph to get it to the top of the tank. We nearly always fill our tanks from the top of the tank. So you're going to have to always have that pressure of that full height of your tank to contend with. The pressures at a tank battery. Typically, our sales contracts are going to be in the 30 to 50 psi range, gas sales. Gas will come in that separator at about 75 psi. It's not uncommon. And that would be a 125-pound rated vessel coming in there. gas pressure at the treater, come from the separator to the treater. The treater pressure will be, say, 10 psi less. And that treaters are lower rated vessels at about 75 psi. And remember then, we're going to an atmospheric tank. And that atmospheric tank pressure is going to be 2 to 4 ounces gauge. At that point, at 2 to 4 ounces, we're going to have to capture it in a vapor recovery system that we let gas out. And that gas will go to a vapor recovery system, so that's going to be the feed pressure on our gas system. In our unconventional wells, they come in at higher flowing pressures. There, instead of coming in at this 30 to 50 range, they're going to be higher, 200 to 500 psi. We may remove the bulk of our gas at a high pressure separator at a satellite and feed that into this battery. Our gas will be 75 to 100 pounds at our low pressure separators. And remember, we've given you data on how much gas to expect after a couple of stages of separation for vapor recovery. And then we've given you data on how much gas to expect coming off a heater treater for a tank battery for vapor recovery. So if we have that vapor recovery unit, say we're in Eagleford, you probably have to have a compressor after your vapor recovery unit to get into a higher line pressure. You can't take 4 ounces of pressure and take it all the way up to 1,000 with a VRU. So you're going to have a compressor more than likely down there for gas vapor. And then for sure you're going to need it if that line pressure coming through there is at 1,000 pounds. You're going to have that additional step-up compressor above the vapor recovery unit. So that's all the free information. Tank battery design, vessel, water injection. Any questions? For what? Your will? Okay, thanks.
How are you starting?